So I have additional forces acting towards the inside there. And so these tensions are the sum of these tensions plus this force from the outside equals what's inside. So as long as the tension holds, the balloon's not gonna pop. And so when you have the high pressure, ultimately what creates the sound
The pressure wave from the air expanding.
no nitpicking here, that doesn't create the sound. That's part of the chain, but what actually creates the sound. If a tree falls in the forest, that riddle. Raise the pressure wave a sound.
Always. I guess when something can hear it.
It has to be perceived. When the pressure wave gets to your eardrum, that's when the sound is created. The pressure wave is created when you pop the balloon, but sound requires perception.
So you're saying if a tree falls in the forest and no one's there to hear it, it does not make a sound.
Correct. And it's a semantics thing, but
So
it's what the powers that be decided.
But it makes a pressure wave,
The pressure wave still exists.
not a sound.
At least I assume the pressure wave still exists. But if nothing's around to perceive it, all states are, and this is what gets into a quantum physics thing, all states are possible until someone observes it and then it collapses down into, depending on how you observed it. All right, so we've talked about the fact that gases are compressible, liquids are not, ish. So if I take a balloon, let's assume a perfect sphere, spherical balloon. And so it's in air, and the radius of the balloon is 1.5 meters. It's a big balloon. It is filled with ideal air. I now take that huge balloon and I dunk it into water. So that the center is now 5 meters below the surface. What is the radius of the balloon? Now, despite what I just talked about, or what was just talked about with the fact that there's tension in the balloon, I'm going to ignore that. Let's assume that the tension coming from the material is negligible. So tension from the latex, whatever it is. So how do you approach it?
Force diagram.
Okay. Actually, force diagram is going to be a little bit more difficult with this one. That force diagram, I like the answer, but I don't think it's the easiest way in this case. All right, let's look at it this way. I take the balloon sitting out in air, 1.5 meters long, I dunk it into the water, and I'm holding it there. And this is why force diagram doesn't really help, is not a lot of information given. other than it's ideal. I guess you could come up with the mass, come up with the acceleration of it, but I don't really care about the acceleration. What's gonna be the same for the balloon here and here?
The amount of air in it,
Okay, let's figure out how much air is in it.
or I guess the mass of the air.
All right. So let's see. How do you find the mass of air?
Because you gotta know the density of the air.
Density of air, Put it down somewhere. It's 1.2 something. Oh, come on. 1.2, the density of air, 1.293 kilograms per cubic meter. This is a very different way than the way I did it, so I'm curious to see where this one ends up.
I guess you need volume.
Okay, what's the volume of the sphere?
Is it 4/3 pi r cubed?
All right, so I got 1.293 times 4/3 pi times 1.5 cubed.
I got 18.279 kilograms.
All right. I did it differently and came up with 16.74. I think ultimately it's not gonna make a difference, but we'll find out. I would expect it as expected to be closer. Well, I guess a reality versus ideal. All right, so I know the mass of the air.
Did you get the same? Yeah.
Yeah. Sorry, no, I was not questioning your calculator skills. I was just trying to figure out what the difference, why it was that far off of the ideal. All right. We've got, all right, so it's now dumped under the water. I have it being pushed on from all sides. With some pressure. What's the pressure acting on it? Assume some average value.
I guess the density of the water times the gravity and then times the depth of the center of mass.
All right, so if we did that one, this is the pressure on it is, you said density of the water times G times the depth.
Yeah, of the center of it.
So 1,000 kilograms per cubic meter times, we'll just put it on Earth to 10 meters per second squared times 5 meters.
50,000 Pascals.
All right. Except that's not, if that's the pressure on that here, there's no pressure on the other one?
Because that's about half of atmospheric pressure, isn't it?
It is about half of atmospheric pressure. I have pressure acting on this one right here. If there were no pressure acting on this from the outside, that thing would keep expanding or explode. So what is the pressure on this one? Ish.
1 atmosphere.
Yeah, or well, roughly 1 times 10 to the 5th pascals.
If you wanted to calculate atmospheric pressure based with that like depth, where is the top of air? Or I guess, is that why you probably can't easily?
Yeah, air decreases in density as you go up, so you probably come up with a decent estimate of at the point at which the amount of air is negligible. I think count that as the top. I think generally outer space is considered to be 100 kilometers from the surface. What's that?
It's convenient.
I suspect that some calculations were done and then they said, 100 kilometers is close enough. Did I address your question?
Yeah.
Okay. All right, so I have this amount of pressure acting on this right here, and so what is the pressure acting on this one then?
The atmospheric pressure plus our
Yeah.
balance.
So that's 100,000, that's 50,000, so 150,000. So I have 150,000 pascals acting on the balloon here. Therefore, well, the number of moles, well, it depends on how you want to go about this. You want the physics or the chemistry version? Either way, I did not throw this in there, but the temperature, assume that the temperature of this water's been sitting out long enough that it's the same temperature as the air. So what we have over here is a constant. Therefore, P1 V1 is equal to P2 V2. P1 was 100,000. V1, but we found mass. Let's see, the volume is mass over density. Make sure that's right. V equals mv. So V is m over, sorry, that's rho over rho. So this is mass over rho is equal to 150,000 times V2. So I got 100,000 times 18.74?
28.
Divided by 1.2,
93, I believe.
that sounds, that's right, is equal to 150,000 V2. So what is the volume of this balloon stuck in the water there?
So that, the 18 over 1.293 is the same as what I recalculated the volume by itself.
Okay. So. You did 18.28 divided by 1.293. And got the volume when it was out,
Well, I did the 2 pi, or 4/3 pi,
r cubed.
yeah.
Okay, what did you get for that?
Well, it was 14.137.166.94, and then the 18.28 over 1.293 is 14.13766, so it's
Okay.
close enough.
Yeah, agreed. Times 100,000 divided by 150,000, or I guess that divided by 1.5.
I got 9.425. I guess meters.
Which is 4/3 pi r, well, r2 cubed.
Uh, 1.310 meters.
All right. So by sticking it under the water like that, again, it's a simplified model. We have shrunk the radius from 1.5 meters to 1.31 meters. And having done it a different way, I came out with 1.31 meters. All right, questions? All right, so let's take these concepts here. Let's create a barometer. A simple barometer is you basically take a tube, fill it with liquid, put a cap on it, or put a pan on it, turn the whole thing over, and then the water in the tube will start to fall, but it won't completely drain out. Theory. So we got a pan right here, I got an upside down amount of some fluid in the pan, and then I've got a vacuum up here, vacuum, let's call it vacuum like, pressure is about 0 Pascal. I don't know if you're familiar with what if. I might have mentioned it before, or you might have seen it before. There was a talk about the glass half full, and you usually think of it that the bottom half is full, the top half is empty, and then someone said, well, suppose the bottom half is empty and the top half is full. What would happen? But he talks about the fact that with that 0 pressure there and gravitational force in the same direction, that water would shoot down to the bottom of the glass with such force it would shatter the glass. But anyway, we have a couple different measurements here. So the distance from here to here, from top of the water or the fluid in the tube to the top of the fluid in the pan, we will call this y. This distance here, y1. It is exposed to the elements, so we would have this just sitting out to let the air pressure be hitting down on it. And what I want to, let's just do the analysis. Let's see, here's my blue. So what I want to do is, let's look at the force diagram. Let's assume that this has an area of gone, A1. So what are the forces acting on the liquid in blue, surrounded by blue? We got our checklist here. FB tongs, Facebook tongs.
Force due to gravity.
All right. So.
Then do we have buoyant force?
Yeah, I'm gonna make it slightly more generalized, and that there's some upward force from the fluid. So I'll just call it F sub fluid. So let's figure out what that force from the fluid is. W kilometer liquid is mg. When I'm dealing with forces being applied by a fluid on a surface, how do I go, what's another way of writing it?
Pressure.
That's along the right lines. So what am I writing here? If I write force is equal to pressure, it's not a true statement. Sorry, I cut you off.
The density of the fluid.
Not there yet.
Okay.
Surface area?
All right, if I just, so what I've heard from you so far is
Oh,
those two statements.
well, pressure times surface.
Okay. We'll get into density of fluid in just a second. All right, so my area is A1.